Picture the ship's small window, and beyond it, nothing but stars that have not moved in your lifetime. Somewhere past all of them sits the center of our galaxy, roughly 26,000 light years away. A number so large, it stops behaving like distance and starts behaving like time. To put it in human terms, light itself, moving at 670 million miles an hour, would need 26,000 years just to make the crossing once. But here's the truth almost nobody talks about. Distance is not what kills you on a trip like this. Distance is just the backdrop. Long before your ship has crossed even a fraction of that gap, something else will have already tried to end you. And it probably won't be the thing you expected. Radiation, gravity, your own bones, the empty space itself, each one waiting patiently for its turn. Tonight, we walk that road in order, one failure at a time, and find out what actually gets you first, second, and last. If you enjoy deep space and science content, do me a small favor. Hit that like button and subscribe to Blackout Universe. It genuinely helps this channel grow, and there is much more like this coming. Make yourself comfortable. Let's begin. We know exactly where we are going. That is the strange part. Most journeys begin with uncertainty, a destination that has to be found, a location that has to be guessed at. This one does not. We have known the address for nearly a century, and the address has a story of its own. One that started not with a telescope pointed at the stars, but with a radio engineer trying to solve a much smaller problem. In 1932, an American physicist named Carl Jansky was working for Bell Telephone Laboratories, trying to track down the source of static that was interfering with transatlantic radio calls. He built a rotating antenna, nicknamed it the merry-go-round, and spent months recording faint hiss after faint hiss. Most of it came from thunderstorms, exactly as expected, but one signal did not behave. It rose and fell on a cycle of 23 hours and 56 minutes, which is not the 24-hour rhythm of the sun. It is the rhythm of the stars. Jansky had accidentally found a radio source coming from deep space, and it was strongest in the direction of the constellation Sagittarius. He had, without meaning to, pointed humanity's attention at the center of its own galaxy for the first time. Consider what that means. The center of the Milky Way was not discovered by someone looking for it. It was discovered by someone trying to fix a phone call. It would take decades for that faint radio hiss to become a number people could actually work with. Through the final decades of the 20th century, astronomers Reinhard Genzel and Andrea Ghez, working independently with separate teams, began tracking individual stars swinging in tight, fast orbits around that same patch of sky. One star, cataloged simply as S2, became the key. It completes a full orbit in about 16 years, at times moving fast enough to cover a meaningful fraction of the speed of light. By watching S2 trace its loop again and again, both teams calculated the mass hidden at the center of that orbit, a mass now understood to be roughly 4 million times heavier than our own sun, packed into a region no larger than our solar system. In 2020, Genzel and Ghez shared the Nobel Prize in Physics for the discovery. What their work confirmed, beyond reasonable doubt, was the presence of a supermassive black hole. We call it Sagittarius a star, and current measurements place it at approximately 26,000 light years from where you are sitting right now. 26,000 light years. In simple terms, if you converted that into miles, you would be looking at a number with 17 digits, 152 quadrillion miles, give or take. Light, the fastest thing that exists, the fastest thing that can exist, would need 26,000 years of uninterrupted travel to cross that gap once. For context, 26,000 years ago, no human being had yet invented writing. The wheel did not exist. Entire ice ages have come and gone in less time than it takes light to make this one crossing. And yet we know the address. We have measured it, confirmed it, mapped the stars that orbit it, watched gas clouds fall toward it, even captured a blurred image of its shadow with a network of telescopes spanning the entire planet. In May of 2022, the Event Horizon Telescope collaboration released that image to the world, the first direct visual evidence of the black hole at the heart of our own galaxy. We have never been closer to understanding where we are going. We have also never been further from getting there, because knowing the destination and surviving the road to it are two entirely different problems. A century of careful observation has told us exactly what waits at the center of the Milky Way. It has told us almost nothing about what waits in between. And that is where this story actually begins. Not with the black hole itself, but with everything standing between here and there. Starting with the one thing that has protected every human being who has ever lived, and the moment you would lose it. Space has a reputation for being empty. It is not. Space, at least the version of space a ship crosses on its way out of the solar system and into the galaxy beyond, is closer to a slow, continuous rain. A rain made of particles instead of water, falling in every direction at once, forever. These particles have a name: galactic cosmic rays, usually shortened to GCRs. They are not something the sun produces. They come from much farther away, likely from the aftermath of supernovae, exploding stars scattered across the galaxy over millions of years, flinging out protons, helium nuclei, and heavier atomic fragments at velocities close to the speed of light. Because they originate outside the solar system, GCRs arrive from every direction, constantly at a low but unrelenting rate. Roughly 3/4 of that rain is made of protons, another fifth or so is helium, and the remainder is heavier particles: carbon, oxygen, iron, each one carrying enough energy to punch through material that would stop an ordinary bullet without slowing down. Here on Earth's surface, almost none of this reaches you. The magnetosphere and the atmosphere, working together, absorb the overwhelming majority of it before it ever gets close to a human body. But once a spacecraft leaves that shelter, the exposure rate does not increase gradually. It jumps. Researchers studying the deep space radiation environment have found that GCR exposure roughly triples once a craft moves fully beyond Earth's protective envelope and into the open solar system. And unlike a sunburn or a scrape, this kind of exposure does not announce itself. There's no pain in the moment, no warning. The particles pass directly through the hull, through the body, through bone and soft tissue alike, and the damage accumulates silently, one collision at a time. To put this in a number the body actually responds to, radiation dose is measured in a unit called the sievert. 1 sievert of exposure across a lifetime is associated with roughly a 5% increase in the risk of fatal cancer. That is not a hypothetical threshold. It comes directly from decades of population studies, including long-term data gathered from survivors of atomic bomb exposure in Japan, cross-referenced against workers exposed occupationally to radiation over years. Space agencies use that relationship to set hard limits on how much dose an astronaut can accumulate across an entire career. For years, the European Space Agency capped its astronauts at 1 sievert total for life. NASA's current standard is closer to 600 millisieverts, a little over half of that figure, reflecting updated science on how much risk is acceptable. Now consider what that means for a voyage that isn't measured in months, but in years, decades, or for a journey toward the center of the galaxy, potentially centuries. A physicist who studies cosmic radiation exposure, Marco Durante, has put the everyday comparison plainly. 1 day spent in deep space delivers roughly the same radiation dose as an entire year spent on the surface of the Earth. 1 day equals 1 year. Say that again slowly, and the shape of the problem becomes clear. A 6-month mission to Mars, well within a human lifespan and well within existing technology, already pushes an astronaut close to their career limit in half a year. A mission that lasts decades does not just approach that limit. It obliterates it, many times over, unless something fundamental changes about how the ship is shielded, how fast it travels, or how long a human body is expected to endure the trip. This is not speculation. It is arithmetic, drawn from real instruments that have already made the journey part way. And it raises an uncomfortable question that the rest of this story has to sit with. If 6 months in space already spends most of a person's radiation budget, what does that mean for a voyage that has to survive tens of thousands of years of exposure just across a single galaxy? The number that matters most in this story is not a distance. It is a dose. Sievert by sievert. The radiation environment beyond Earth quietly writes a limit on how long any human body can survive the journey, and that limit turns out to be far stricter than most people assume. The most complete real-world measurement of this problem came from an unlikely source, a car-sized rover sitting on the surface of Mars. Curiosity carries an instrument called the Radiation Assessment Detector, RAD for short, which began recording data the moment it left Earth in 2011 and continued through its 8-month cruise to Mars and its years exploring the Martian surface. When scientists finally compiled that data into a full mission profile, the results were specific and sobering. A round-trip crewed mission to Mars, structured as a 180-day outbound cruise, a 500-day stay on the surface, and a 180-day return, would expose an astronaut to a cumulative dose of just over 1 sievert. 1 sievert. The same number that used to represent an entire career's allowable limit, absorbed in less than 2 years, for a trip that, on the scale of this story, barely leaves the driveway. Consider what that comparison actually means. Mars, at its closest approach to Earth, sits roughly the same distance from us as a few light minutes. The center of the galaxy sits 26,000 light years away. If a round trip to our nearest planetary neighbor already consumes a full career's radiation budget, the radiation cost of reaching the galactic center is not simply larger. It exists in an entirely different category of problem, one that current biology and current shielding technology were never designed to solve. It helps to separate 2 different kinds of exposure because they carry different consequences. There is acute exposure, a single large dose delivered over a short period, the kind associated with a major solar flare or a coronal mass ejection erupting from the sun. A severe enough acute dose in the range of several sieverts delivered within hours would produce radiation sickness with a very high chance of death within days or weeks, regardless of medical care. Then there is chronic exposure, the slow, steady accumulation from galactic cosmic rays. Sievert fractions building up month after month, year after year in the background, without ever producing an obvious symptom until the cancer risk, the cardiovascular risk, and the neurological risk have already compounded into something serious. A crossing to the galactic center would involve both. Chronic exposure would be constant, unavoidable, and cumulative across the entire duration of the voyage, likely for generations of crew, each life adding its own fraction to a dose that never fully resets. Acute exposure would be an ever-present possibility, one unpredictable solar-style event away from disaster, except now originating not just from a single star, but from the broader galactic environment the ship would be crossing. Neither category has a known solution today. There's no shielding material currently available that fully blocks the highest energy galactic cosmic rays, and no known biological countermeasure that reverses the cellular damage those particles cause as they pass through tissue. What this means in practice is that radiation alone, without factoring in anything else on this list, already renders a direct human crossing to the galactic center functionally incompatible with the biology we currently have. Not difficult, not risky. Incompatible, in the same way that breathing underwater without equipment is incompatible with human lungs. The dose accumulates whether or not anyone chooses to think about it. And unlike almost every other hazard in this story, there's no way to simply wait it out, slow down, or route around it. The rain falls the entire way. The obvious answer to a radiation problem is to build a thicker wall. More metal, more mass, more material standing between the crew and the particles trying to reach them. It is the same instinct that leads people to wear a heavier coat in a colder wind. And for a narrow range of threats, it actually works. The trouble is that galactic cosmic rays do not behave like a cold wind. Past a certain point, adding shielding does not just fail to help, it makes things worse. To understand why, it helps to know what shielding is actually doing at the level of individual particles. When a high-energy proton or heavy nucleus slams into a wall of aluminum or polyethylene or any other shielding material, it does not simply stop and get absorbed the way a bullet might lodge in a block of wood. Instead, it collides with the atoms inside that material and shatters, producing a spray of secondary particles, smaller fragments, secondary protons, neutrons, gamma rays, all moving onward into the spacecraft, into the crew compartment, into the human body waiting on the other side. This is called a nuclear cascade, and it means that a wall meant to stop radiation can, under the wrong conditions, become a source of radiation itself, converting one dangerous particle into several less energetic, but still harmful ones. For lower energy radiation, more shielding still helps on balance, because the material absorbs more than it generates. But galactic cosmic rays include a component of extremely high energy heavy nuclei, sometimes called HZE particles, for high charge and energy, and these do not behave the same way. Researchers modeling shielding requirements for a crewed Mars mission found something the engineering instinct did not predict. There's a sweet spot, a shielding thickness of roughly 30 grams per square centimeter that offers close to the best available protection. Below that thickness, you're simply not blocking enough of the primary radiation, but above roughly 40 grams per square centimeter, particularly during periods of high solar activity. Additional shielding actually increases the dose reaching the crew, because the cascade effect from the highest energy particles starts to outweigh the benefit of the extra absorption. In simple terms, there is a point past which building a thicker wall stops protecting you and starts hurting you instead. This creates a hard ceiling on what engineering alone can achieve. It's tempting to imagine that a sufficiently determined, sufficiently wealthy civilization could simply keep adding mass to a spacecraft's hull until the radiation problem disappeared. The physics does not allow that option. Past the optimal thickness, you are not spending resources for diminishing returns. You are actively spending resources to make the problem worse. And even at the optimal thickness, that shielding only manages to reduce dose, not eliminate it. Advanced concepts using theoretical nuclear thrusters, paired with fast transfer trajectories that minimize total time in transit, have been estimated to bring total mission dose down to somewhere between 0.2 and half a sievert for a Mars-scale trip. Time to launch during a period of high solar activity, when the sun's own magnetic field helps deflect a portion of the incoming galactic cosmic ray flux. That is meaningfully lower than the 1 sievert figure from earlier missions. It is still not zero, and it is still calculated for a trip that, measured against a journey to the galactic center, barely qualifies as leaving the front porch. What this tells us, stated plainly, is that shielding can manage the radiation problem for a mission measured in months. It cannot solve it for a mission measured in centuries, or millennia, or the tens of thousands of years a direct crossing at anything resembling currently achievable speeds would actually require. There's no thickness of wall, no clever material, no amount of engineering effort that changes the fundamental physics of how these particles interact with matter. At some point, the ceiling is not an obstacle to be worked around. It is simply where the problem ends and the limits of physics begin. And this is only the first hazard on the list. Radiation alone, even before factoring in anything else waiting along the route, already establishes that a direct, continuously crude crossing to the galactic center is not simply difficult with current technology. It sits outside what current technology, or any technology built on the same physical principles, could ever be expected to achieve. Which raises the next uncomfortable question. If the ship itself cannot fully protect the people inside it, what happens to those people's bodies over the months, years, and decades they would spend absorbing what does get through? Before returning to the body and what space does to it, it's worth pausing here, stepping back from the equations and the sievert counts, and returning to the people who first made this entire story possible. Because behind every number in the script is a room, a desk, an instrument, and someone paying very close attention to something almost everyone else had overlooked. Return for a moment to Karl Jansky's rotating antenna in 1932 out on a New Jersey field belonging to Bell Telephone Laboratories. He was 26 years old, an engineer without a background in astronomy, assigned a problem that had nothing to do with the stars. Figure out what was causing static on transatlantic phone calls. His antenna, mounted on wheels salvaged from a Model T Ford, rotated slowly on a track, sweeping the sky over and over, recording faint hiss from every direction. For months, the pattern matched thunderstorms exactly as expected. Then it didn't. a separate, fainter signal rose and fell on a cycle just 4 minutes short of 24 hours, a rhythm that meant it was tracking the stars, not the sun. Jansky spent nearly a year confirming what he was seeing before he was confident enough to publish. When he finally did, in 1933, the discovery made front-page news around the world, not because anyone yet understood its significance, but because the idea of radio signals arriving from outer space captured the public's imagination immediately. Jansky himself wanted to build a larger antenna and keep investigating. Bell Labs, satisfied that the phone call static had been explained, reassigned him to other projects. The man who discovered the radio source at the heart of the galaxy never got to study it further. It would take decades and an entirely different kind of instrument to turn that faint signal into something resembling a full picture. In the final years of the 20th century and the opening years of the 21st, two research teams, one led by Reinhard Genzel in Germany, the other by Andrea Ghez in the United States, independently began the painstaking work of tracking individual stars near the galactic center using ground-based telescopes fitted with adaptive optics, a technology that corrects, in real time, for the blurring caused by Earth's own atmosphere. This was not a quick observation. It required returning to the same patch of sky year after year for the better part of 2 decades, charting the position of faint stars against the glare of everything around them, waiting for enough of an orbit to trace a curve. Picture what that actually looked like in practice. Astronomers gathering data across entire careers, watching one star in particular, S2, complete a single loop that takes roughly 16 years, patiently building a picture too slow for any one person to witness in full without decades of dedication. When the orbit finally closed, the calculation fell out of the data cleanly. Something with the mass of roughly 4 million suns was sitting at the focus of that orbit, in a space too small and too dark to be anything other than a black hole. In 2020, the Nobel Prize in Physics was awarded jointly to Genzel and Ghez for that work, alongside Roger Penrose for his separate, earlier theoretical contributions proving that black holes are a robust prediction of general relativity, not a mathematical curiosity. There is something worth sitting with in this history. None of it happened quickly. None of it happened by accident twice. It happened because people were willing to watch the same small patch of sky for years, decades, entire careers, waiting for a pattern too vast to reveal itself in a single human lifetime's worth of casual glances. In that sense, the story of how we found the galactic center is itself a kind of preview of the story we're telling tonight. Patience measured in decades, rewards measured in fractions of understanding, and an object at the center of it all that, even fully mapped, remains almost entirely beyond reach. We return now to the ship and to the crew inside it, and to what all that measured, patient, decades-long science tells us is actually happening to a human body across a journey that would dwarf even Jansky's, Genzel's, and Gez's careers combined. Gravity is easy to take for granted precisely because it never stops. It has been pulling on every cell in your body since before you were born, and your skeleton, your muscles, your entire physical structure evolved under its constant, unbroken pressure. Remove that pressure, even briefly, and the body does not simply relax. It begins, almost immediately, to forget what it was built for. Start with bone. human bone is not a static scaffold. It is living tissue, constantly being broken down and rebuilt in a cycle called remodeling, a cycle that depends heavily on mechanical load, the ordinary, everyday stress of standing, walking, lifting, simply existing under Earth's gravity. In microgravity, that load disappears, and the remodeling cycle falls out of balance. Bone-dissolving cells continue their work at close to the normal rate, while bone-building cells slow down, no longer receiving the mechanical signal that tells them to keep pace. NASA's own long-term data, drawn from astronauts aboard the International Space Station, puts the result at a loss of roughly 1 to 2% of bone density per month, concentrated most heavily in the weight-bearing bones, the spine, the hips, the legs. To put that in human terms, 6 months in orbit can leave an astronaut with bone density losses comparable to what a postmenopausal woman on Earth might experience over an entire year of natural age-related decline. The European Space Agency has drawn the comparison even more directly, noting that after 6 months in space, an astronaut's bone condition can resemble the osteoporosis typically seen in elderly women, compressed into half a year instead of decades. Muscle follows a similar pattern, for similar reasons. Without gravity's resistance, without the ordinary daily work of standing and walking and simply holding the body upright, muscles begin to atrophy almost immediately. On short missions, astronauts have measured muscle loss in the range of 10 to 20%, even with dedicated exercise regimens built into their daily schedule, specifically to fight this decline. Without any countermeasures at all, researchers estimate that figure could climb to 50% or more on sufficiently long missions. A person returning not just weaker, but structurally diminished, in ways that resistance training after the fact can only partially reverse. Consider what that means for the very beginning of a hypothetical crew's exposure to deep space, before any of the other hazards in this story have even had time to compound. The astronauts we have already sent to the International Space Station for missions typically lasting 4 to 7 months represent some of the best documented, most carefully monitored human bodies in history. Every meal is tracked, every exercise session is logged, bone scans are taken before flight, during flight where possible, and for months after return. And even under that level of care, even with hours of daily resistance and cardiovascular exercise built directly into the mission schedule specifically to counteract this decline, the loss still happens. It is slowed. It is managed. It is not eliminated. What this tells us is that the body does not require a hostile environment to begin failing. It does not require solar flares or cosmic ray bombardment or any of the more dramatic hazards already covered in this story. It only requires the removal of the one force that has shaped every vertebrate skeleton for hundreds of millions of years of evolutionary history. Gravity is not a background detail of life on Earth. It is a load-bearing requirement of the human body itself, and the moment that load disappears, the body begins, cell by cell, quietly renegotiating the terms of its own existence. This raises an obvious question, one that becomes considerably more pressing once the timescales involved stop being measured in months and start being measured in decades or centuries, or the kind of multi-generational span a true galactic crossing would require. If 6 months of careful, monitored, well-resourced spaceflight already produces measurable structural decline, what happens to a body, or to a lineage of bodies, passed from one generation of travelers to the next, across a journey with no clear endpoint in sight. 6 months of bone and muscle decline is a problem NASA already understands, tracks, and partially manages. It is not, however, the problem this journey actually poses. The real question is what happens when that same biological decline is no longer capped at 6 months or even 6 years, but stretched across a timescale with no natural endpoint. A voyage measured not in a single crew's working lifetime, but potentially across many. Start with what is actually known, because that boundary matters. The longest single continuous human space flights on record run close to a year. Cosmonaut Valery Polyakov's 437-day mission aboard the Mir space station remains among the longest ever completed, and even that mission required extensive medical monitoring and a lengthy, difficult physical rehabilitation once he returned to Earth's gravity. Beyond that rough 1-year mark, there is no direct human data at all. Every projection past that point is an extrapolation, built from shorter missions and applied forward, and honest science treats it as exactly that, an informed estimate, not a certainty. What the extrapolation suggests, though, is not encouraging. If bone density loss continues at anything close to the observed rate of 1 to 2% per month, without ever reaching a plateau, a mission lasting several years could theoretically produce losses in the range of 30 to 60% of original bone density. Whether the body's remodeling process eventually finds some kind of new equilibrium at extreme durations, or whether the decline simply continues unchecked, remains one of the genuinely open questions in space medicine today. Researchers studying post-flight recovery have found something equally sobering on the other end of the process. Astronauts returning from missions longer than 6 months show incomplete bone recovery even a full year after landing back on Earth, with reductions in bone strength and internal bone structure that researchers have compared to a decade or more of ordinary, earthbound aging compressed into a period measured in months. Bone and muscle are not the only systems affected either. The European Space Agency has documented a higher rate of early onset cataracts among astronauts who have spent extended time in space, believed to be linked to radiation exposure interacting with the lens of the eye over time. Cardiovascular changes have also been observed. Shifts in how the heart handles fluid distribution without gravity pulling blood toward the legs, changes that researchers are still working to fully characterize across longer mission durations. And the immune system itself appears to behave differently in microgravity, with some studies noting altered activity in certain white blood cell populations, changes whose long-term practical consequences for infection resistance across a multi-year mission remain an active area of ongoing research rather than a settled conclusion. It's worth pausing on that distinction because it matters for how we tell this story honestly. Some of what happens to the body in deep space is well established, repeatedly measured, and essentially certain. The bone loss figures, the muscle atrophy figures, these come from dozens of missions and hundreds of astronauts, cross-checked against Earth-based aging data. Other effects, particularly the ones that would only fully emerge across multi-year or multi-decade exposure, remain genuinely open questions, the subject of active research rather than settled fact. A responsible accounting of this journey has to hold both of those truths at once, what we know with confidence and what we do not yet know at all, because no human being has ever stayed in space long enough for us to find out. What can be said with confidence is this: even under the most careful, most resourced, most medically monitored conditions currently achievable, the human body was built for a world with gravity, and every month spent without it appears to extract a cost that current science cannot fully reverse. Stretch that exposure from months into years, from years into decades, from decades into the kind of timescale a true crossing of the galaxy would demand, and the body is not simply inconvenienced. It is being asked to survive in conditions its 400 million year evolutionary history never once prepared it for. Bone and muscle are only the beginning of that story. The next hazard does not wait for the body to weaken first. It is already outside the hull, moving at speeds that make even the fastest human-made object in history look motionless by comparison. There's a particular kind of danger that only exists at extreme speed, one that has nothing to do with radiation and nothing to do with the slow erosion of bone and muscle. It is the danger of simply running into something. Not an asteroid, not a planet. Something far smaller, a grain of dust, a fleck of rock no larger than a crumb. And at the right velocity, that fleck becomes as destructive as an artillery shell. In ordinary spaceflight, this danger already exists, and it is already taken seriously. Micrometeoroids, tiny particles of rock and metal left over from the formation of the solar system, drift through space at typical speeds in the tens of kilometers per second. That may not sound dramatic until you translate it into more familiar terms. Tens of kilometers per second is roughly 70 times faster than a rifle bullet. At that velocity, even a particle smaller than a grain of sand carries enough kinetic energy to punch through a spacecraft's hull, puncture a pressurized module, or short out sensitive electronics on contact. This is precisely why the International Space Station is built with what engineers call a Whipple shield, named after the American astronomer Fred Whipple, who proposed the concept decades ago. It works by placing a thin outer layer of material a short distance from the main hull, so that an incoming particle shatters into a wider, less concentrated spray on impact with the outer layer, spreading its energy across a larger area before it ever reaches the layer that actually holds the ship's air in. That is the danger at ordinary interplanetary speeds. Now raise the ship's velocity toward a meaningful fraction of the speed of light, and the entire problem changes in kind, not just in degree. At relativistic speeds, a spacecraft is no longer just dodging occasional rocks. It is plowing directly into the interstellar medium itself, the extremely thin scattering of gas and dust that fills the space between stars. Individually, these particles are almost nothing. Atoms and molecules spread so sparsely that a cubic centimeter of interstellar space might contain only a single hydrogen atom. But a ship moving at a significant fraction of light speed does not encounter these particles gently. Researchers who have modeled the physics of hypervelocity dust impacts at relativistic speeds have found that a single collision with even a microscopic grain at those velocities releases kinetic energy on the order of several kilotons of TNT equivalent. An explosion concentrated into a point smaller than a pinhead, striking the leading edge of the ship over and over, every second, for the entire duration of high-speed travel. Consider what that actually means for the physical structure of a starship. It is not one dramatic impact to brace for. It is a continuous bombardment, a sandstorm of individually survivable but collectively catastrophic strikes, each one melting, cratering, and slowly eroding whatever material happens to be facing forward. Engineers studying this problem for theoretical relativistic spacecraft have concluded that any leading surface exposed to this environment for an extended high-speed cruise would need to survive a level of continuous erosion and radiative damage far beyond anything current materials science has tested, let alone solved. Multi-layered Whipple-style shielding, of the kind already used on the International Space Station, remains the primary proposed defense, but shielding designed to handle occasional strikes at tens of kilometers per second is a fundamentally different engineering problem than shielding designed to survive a continuous kiloton-scale bombardment sustained over years or decades of relativistic cruising. There's also a deeper irony buried in this hazard, one worth sitting with for a moment. Every proposed solution to the radiation problem, and every proposed solution to the sheer scale of the distance involved, points toward the same answer: go faster. Higher velocity shortens the subjective duration of the trip, reduces total radiation exposure over time, and brings the destination within a survivable window. But going faster does not just fail to solve the dust problem, it actively makes it worse, because kinetic energy scales with the square velocity. Doubling a ship's speed does not double the danger of a dust strike, it roughly quadruples it. The very acceleration that promises to save the crew from one hazard simultaneously intensifies an entirely different one, turning empty space itself into an increasingly hostile environment the faster a ship tries to cross it. This is the shape of the problem the rest of this story keeps returning to. Space does not present a single obstacle to overcome. It presents a set of competing constraints, where the solution to one hazard actively worsens another, and no available technology resolves all of them simultaneously. The interstellar medium, thin as it is, becomes something closer to a wall the faster you try to pass through it. And that wall is not the only way the emptiness between stars turns hostile at extreme velocity. There is a second effect, stranger still, waiting in the space between the atoms. There is a second consequence of extreme speed, separate from the dust and gravel scattered through space, and it is stranger because it comes from something that isn't solid at all. It comes from gas, the thinnest, most diffuse gas imaginable, individual hydrogen atoms, drifting through the space between stars, spaced so far apart that under ordinary circumstances, they might as well not exist. At relativistic speeds, they stop being nothing and start being a threat in their own right. To understand why, it helps to think about what hitting something actually means at different speeds. A ship cruising through the solar system at a typical spacecraft velocity, a handful of kilometers per second, essentially never notices interstellar hydrogen atoms. They are too sparse, too light, and the relative speed of any encounter is too low to matter. But push that same ship toward a meaningful fraction of the speed of light, and the physics of the encounter changes entirely. At sufficiently high velocity, above roughly 30% of the speed of light according to researchers who have modeled this problem, the individual hydrogen nuclei a ship encounters are no longer passive obstacles. From the reference frame of the ship, they arrive as a stream of relativistic particles, indistinguishable in their effects from a beam of cosmic radiation. The interstellar medium, in other words, does not just contain radiation. At high enough speed, it becomes radiation, generated directly by the act of traveling through it. Consider what that means in practical terms. A crew traveling at a significant fraction of light speed would not simply be passing through empty space, punctuated by occasional random hazards. They would be flying directly into a wind, one made of subatomic particles instead of air, striking the ship continuously. The intensity of that wind scaling upward the faster the ship tries to go. Physicists studying the feasibility of relativistic interstellar travel have calculated that beyond a certain velocity threshold, this self-generated radiation source could rival or exceed the background dose from galactic cosmic rays covered earlier in this story, meaning that even a perfectly shielded ship, one somehow immune to every external radiation source in the galaxy, would still generate a hazardous radiation environment purely as a side effect of its own velocity. There is a further complication buried inside the same physics, one that involves the individual atoms making up the ship's own hull. Some researchers modeling high-speed interstellar cruise have found that repeated collisions with interstellar particles at relativistic speed produce a slow cascade of secondary particles inside the leading structure of the ship, gradually degrading the atomic structure of whatever material happens to be facing forward. The rate of this degradation, according to these models, remains modest compared to the total number of atoms in a solid structure, but it adds yet another slow, compounding form of wear to a list of hazards that already includes cosmic radiation, bone loss, and dust impacts, each one operating on its own timescale, each one chipping away at the ship and its crew simultaneously for the entire duration of the journey. What ties all of these threads together is a single uncomfortable pattern. Every attempt to solve one problem on this journey creates or worsens another. Slower travel reduces the intensity of dust strikes and interstellar wind, but stretches the total duration of radiation exposure across a longer timeline and extends every other biological hazard covered earlier in this story across more years, more decades, more centuries. Faster travel shortens that timeline, but intensifies the dust hazard by the square of velocity, and above a certain threshold, transforms the interstellar medium itself from a nearly frictionless vacuum into an active source of radiation. There's no speed at which all of these variables improve simultaneously. There is only a trade-off, a shifting balance between different flavors of the same fundamental problem, and no version of that balance that fully protects a human crew across a journey of the scale this story is describing. For context, remember that everything discussed in this section and the one before, it assumes a ship has somehow already solved the most basic problem of all: how to reach a meaningful fraction of the speed of light in the first place. That problem, it turns out, is not a matter of engineering difficulty. It is a matter of energy, fuel, and a piece of 19th century mathematics that no amount of ambition has ever found a way around. Every hazard covered so far in this story assumes something that has not yet been addressed directly: a ship capable of reaching a meaningful fraction of the speed of light in the first place. It is worth stopping here and asking the most basic question a journey like this actually depends on. Not how do we survive the trip, how do we even begin it? And the honest answer, rooted in more than 3 centuries of established physics, is considerably bleaker than most people assume. The starting point is a piece of mathematics dating back to the late 19th century, formalized by the Russian scientist Konstantin Tsiolkovsky in 1903, now known simply as the rocket equation. It describes, with total precision, the relationship between how much a rocket can change its velocity, how fast it expels its exhaust, and how much of its total mass has to be fuel rather than payload. The relationship is logarithmic, which sounds like a small mathematical detail until you see what it actually means in practice. Every additional increment of speed costs progressively more fuel than the increment before it, and that cost compounds so aggressively that, past a certain point, adding more fuel barely helps at all, because the fuel itself has mass, and that mass has to be carried and accelerated along with everything else. Consider what this means for the most familiar form of rocket propulsion available today: chemical propulsion, the same basic principle that powered the Saturn V and every crewed mission since. Chemical rockets typically achieve an exhaust velocity in the range of 4 to 5 kilometers per second. Physicists who have run the rocket equation forward, using genuinely extreme assumptions about how much fuel a ship could theoretically carry, have found that even with an amount of propellant mass equivalent to a significant fraction of everything in the observable universe, chemical propulsion alone could not push a single proton, let alone a spacecraft, beyond roughly 0.2% of the speed of light. Not through any engineering failure, through the mathematics itself. The relationship between fuel mass and achievable velocity simply does not bend far enough, no matter how much material is thrown at the problem. To put that number in human terms, consider Voyager 1, humanity's fastest and most distant spacecraft, launched in 1977 and still transmitting today. Voyager 1 travels at roughly 17 kilometers per second relative to the Sun, a genuinely impressive speed by any everyday standard, fast enough to cross the continental United States in under 4 minutes. And yet, at that velocity, Voyager 1 would need approximately 17,000 years just to cover a single light year. The nearest star system to our own Sun, Proxima Centauri, sits a little over 4 light years away. Reaching it at Voyager's speed would take on the order of 70,000 years. The center of the galaxy sits 26,000 light years distant. At Voyager's pace, the arithmetic stops being merely large and starts becoming almost meaningless. Several 100 million years, a span of time longer than the age of most complex animal life on Earth. This is why serious researchers studying interstellar propulsion abandon chemical rockets almost immediately and turn instead toward more exotic alternatives: nuclear thermal propulsion, nuclear pulse propulsion, fusion-based designs, ion engines powered by enormous reactors. Each of these improves on chemical propulsion's exhaust velocity by a meaningful factor. None of them comes close to solving the underlying problem. Physicists analyzing the theoretical limits of these systems have found that fusion propulsion, one of the more promising options, still converts less than 1% of its fuel's rest mass into usable propulsive energy, a fundamental inefficiency baked into the physics of the fusion reaction itself. Ion engines can achieve extremely high exhaust velocities, but only by expelling propellant at an extremely low rate, meaning they produce enormous efficiency paired with almost negligible thrust, useful for slow, patient maneuvers within a solar system, but essentially unusable for rapidly accelerating a crewed vessel across galactic distances within a survivable time frame. there's a second layer to this problem that rarely makes it into the popular imagination, and it involves not the engine, but everything the engine has to carry along with it. A rocket does not simply need fuel. It needs a structure to hold that fuel, a way to keep it stable across years or decades of travel, and, in the case of anything beyond simple chemical propellant, shielding, cooling systems, and containment mechanisms whose own mass has to be factored back into the same unforgiving equation. Engineers who study staged propulsion designs for relativistic travel describe this as a compounding tax. Every kilogram of containment hardware is itself a kilogram that has to be accelerated, which requires more fuel, whose own tank and cooling system adds more mass, whose acceleration requires still more fuel again. In practice, this means that even propulsion systems with excellent theoretical performance on paper often see their real-world achievable velocity cut dramatically once the full mass of a genuinely functional, radiation-shielded, multi-decade durable spacecraft is accounted for, rather than an idealized point mass with unlimited structural integrity. What all of this converges on is a single, unavoidable conclusion. Reaching relativistic speed, the kind of speed that would make a journey to the galactic center even theoretically survivable within a human-relevant timescale, requires a fuel source categorically different from anything currently available. Not a better version of what we have. Something else entirely, operating on a fundamentally different physical principle, one where a much larger fraction of the fuel's own mass converts directly into propulsive energy. There is, in fact, exactly one candidate physicists take seriously for this role, one substance capable of releasing close to the theoretical maximum amount of energy per unit of mass that physics allows. It is also, without exaggeration, the single most dangerous material human beings have ever theorized about creating and storing on board a crewed vessel. If chemical propulsion, nuclear propulsion, and fusion all fail to reach relativistic speed within a survivable mass budget, physics leaves exactly one remaining candidate that theoretically closes the gap: antimatter. It is, on paper, the most powerful fuel physics allows. It is also, in practice, one of the most difficult and dangerous substances human engineering has ever seriously proposed carrying aboard a crewed vessel. Start with why antimatter works at all, because the underlying principle is almost unsettlingly simple. Ordinary matter, brought into contact with its antimatter counterpart, does not burn or react the way chemical fuel does. It annihilates completely, converting essentially all of the combined mass directly into energy, following the same relationship Einstein described in his 1905 paper on special relativity: energy equals mass times the speed of light squared. Chemical rockets convert a tiny fraction of a percent of their fuel's mass into usable energy. Fusion, even in its most optimistic theoretical form, converts less than 1%. Matter-antimatter annihilation, by contrast, converts nearly all of it. Gram for gram, it is the most energy-dense fuel that the laws of physics permit, a source of propulsive energy so far beyond chemical or nuclear alternatives that it exists in an entirely different category of magnitude. That efficiency is exactly why serious physicists modeling relativistic spacecraft keep returning to it, despite the enormous practical obstacles involved. Researchers studying antimatter-based rocket designs, including proposed Pion rockets that harness the charged particles produced by proton-antiproton annihilation have calculated that antimatter propulsion is the only chemical or nuclear adjacent option capable of theoretically reaching cruising speeds in the range of half the speed of light or higher, the kind of velocity that would be required to make a journey of tens of thousands of light years fall within anything resembling a human-relevant timescale. But the same annihilation reaction that makes antimatter so powerful also makes it extraordinarily dangerous to actually use. When a proton and an antiproton annihilate, the reaction does not convert cleanly into a smooth stream of usable thrust. A significant fraction of the reaction, well over a third by most calculations, and in some reaction pathways more than 60%, is released not as directed kinetic energy, but as gamma radiation, along with a spray of short-lived particles called pions, scattering outward in every direction. Gamma rays are among the most penetrating, most biologically damaging forms of radiation known, capable of passing through many centimeters of shielding material that would easily stop other forms of radiation entirely. A ship burning antimatter for propulsion would therefore need to solve two radiation problems simultaneously: the external cosmic radiation environment already covered earlier in this story, and an internal radiation source, generated by its own engine, potentially just as hazardous, sitting a short distance from the crew compartment for the entire duration of active thrust. Then there is the problem of simply keeping the fuel intact before it's ever used. Antimatter cannot be stored in an ordinary container because any contact with normal matter triggers immediate annihilation. Physicists have proposed storing it as frozen antihydrogen, suspended and levitated inside a magnetic containment field, kept in a state cold enough and isolated enough that it never physically touches the walls of its own storage vessel. Any failure of that magnetic field, even briefly, would release the stored antimatter's energy essentially all at once, producing a release event bearing little resemblance to a controlled burn and considerably more resemblance to a bomb. Every gram of antimatter fuel a ship carries, in other words, is simultaneously its most powerful asset and its single greatest point of catastrophic failure. A razor's edge, the entire mission would have to walk continuously for years or decades without a single containment failure anywhere along the way. There is also a much simpler, more immediate problem, one that has nothing to do with the physics of the reaction itself. We do not currently know how to produce meaningful quantities of antimatter at all. The total amount of antimatter humanity has ever created across every particle accelerator experiment in history amounts to a quantity too small to weigh on any practical scale, produced at staggering energy cost and existing for mere fractions of a second before annihilating again. Scaling that production up to the tons of antimatter a crude relativistic mission would require represents a genuinely open scientific and engineering question, one with no known solution using any technology that exists today or that appears clearly achievable on any near-term horizon. This is not a minor footnote. It is, in many ways, the central obstacle standing between antimatter propulsion as a mathematical possibility and antimatter propulsion as an actual buildable engine. To put the production problem in more concrete terms, physicists have estimated that generating even a single gram of antimatter using current particle accelerator technology would require an amount of energy comparable to a substantial fraction of a year's total electricity output of a country. and would still take years or decades of continuous operation to accumulate. A crude relativistic mission, by most engineering estimates, would require not grams but tons of antimatter fuel. The gap between what current technology can produce and what such a mission would actually require is not a matter of scaling up existing methods. It is closer to the gap between lighting a candle and igniting a star, a difference not of degree, but of category. Taken together, these four problems, the radiation released by the engine itself, the catastrophic risk embedded in the storage system, the almost complete absence of any known method for producing antimatter at meaningful scale, and the sheer energetic cost of the small amounts we can produce today, describe a fuel source that is simultaneously the best theoretical option available, and, by a wide margin, the most dangerous. Even in the most optimistic version of this story, the version where every engineering challenge eventually finds a solution, antimatter propulsion does not remove risk from the journey. It relocates it from the vacuum of space outside the hull to a containment system a few meters from the crew, running continuously for as long as the engine needs to burn. And even if every one of those obstacles were somehow solved, cleanly and completely, there remains one more consequence of high-speed travel that no amount of engineering can touch at all, because it is not a problem of materials or fuel. It is a property of time itself, and of what happens to it once a ship gets close enough to the speed of light for physics to start behaving strangely. Step back for a moment from the engines, the fuel calculations, the radiation counts, and simply consider the space itself. Not what moves through it, not what threatens a ship crossing it. Just the space in its raw, almost incomprehensible scale, because everything discussed so far in the story takes place inside a distance that resists ordinary description. 26,000 light years. It has been said several times already in the script, and it will be worth returning to again before the end, because numbers this large have a way of sliding past the mind without actually registering. Try it a different way. If the entire 26,000 light-year journey were compressed down to the length of a single football field, the distance from Earth to the Sun, 93 million miles, would occupy less space than the width of a human hair. The distance to the nearest star beyond our own sun, over 4 light years, would still only stretch a few inches along that same field. Almost the entire length of the field, nearly its full 100 yards, would represent the empty gulf still remaining, star after star after star, scattered so thinly across that distance that a ship could cross the entire remaining length and encounter, on average, only a handful of solar systems along the way. This is the part of the story that a list of hazards can obscure if you move through it too quickly. Radiation, dust, fuel limits, bone loss. Each of these is a real, measurable, individually survivable or not problem. But laid end to end, stretched across the true scale of the distance involved, they stop being individual hazards and start becoming something closer to a physical law of the journey itself. Not an obstacle course, with a finish line waiting at a fixed, known point in time, a gauntlet with no natural end, extended across a span of space so vast that even light, moving at its full, unbroken, maximum possible speed, requires 26,000 years simply to make the crossing once in a straight line, without slowing down, without stopping, without deviation. Consider the civilizations that might exist, or might have existed, somewhere along that path. The stars a ship would pass on its way toward the galactic center are not evenly distributed empty space punctuated by occasional light. Near the outer regions of the galaxy, in the relatively sparse spiral arm where our own solar system sits, stars average several light years apart from one another. Vast oceans of darkness between each point of light. Deeper toward the center, that spacing tightens considerably, the density of stars increasing the closer a ship gets to the galactic core. A detail the story returns to in more depth later, once the destination itself comes into view. For now, it is enough to hold both facts simultaneously. The distance is almost incomprehensibly vast, and yet within that vastness, virtually nothing exists. Empty space, overwhelmingly, is exactly what it sounds like. Empty. And within that emptiness, every hazard described so far in the story does not simply happen once. It repeats over and over for the entire duration of the crossing, whatever that duration turns out to be. The radiation does not pause partway through. The dust does not thin out for a stretch of easier travel. The body does not get a rest period from gravity's absence. Every single hazard operates continuously for years, decades, centuries, however long the ship remains in transit, layered on top of every other hazard, compounding rather than alternating. This is perhaps the truest description of what a journey to the galactic center actually is. Not a single dangerous moment to survive, the way a person might survive a car accident or a diagnosis. A dangerous environment to inhabit continuously for a span of time that dwarfs any single human life, any single human generation, any single human institution that has ever managed to sustain itself across comparable stretches of history. It is worth remembering, too, that this same emptiness, the very thing making the journey so dangerous, is also the reason we can see the destination at all. Light from the galactic center reaches Earth precisely because the space between here and there is mostly clear, mostly uninterrupted, mostly nothing. The same vacuum that starves a traveling ship of any possibility for rescue, resupply, or course correction is the reason astronomers were ever able to point an antenna at that patch of sky in the first place and find something worth investigating. The emptiness that kills is the same emptiness that reveals. There is no version of this story where the two are separable. There is one more way to feel this scale, perhaps the most direct of all. 26,000 years ago, the last ice age had not yet reached its coldest point. The animals that would later be domesticated into dogs were only beginning to separate from wild wolf populations, according to genetic estimates. No city had been built. No written word had been recorded anywhere on Earth. Every empire, every language, every technology, every war, every book, every recorded human thought that has ever existed happened entirely within a span of time shorter than the one light itself needs to cross the distance this ship is attempting. Put a traveler on that ship at anything less than the speed of light, and the arithmetic only grows more extreme from there. The distance is not simply large. It is large enough to make the entirety of recorded human history look, by comparison, like a single afternoon. From here, the picture shifts once more. Everything covered until this point involves problems a fast enough, well-engineered enough ship might, in some theoretical future, actually solve. Better shielding, more efficient fuel, structural improvements to survive dust erosion. But the next hazard on this list is different in kind from everything before it, because it cannot be engineered around at all. It emerges directly from the geometry of space and time themselves, the moment a ship's velocity approaches the speed of light, closely enough for physics to stop behaving the way it does in ordinary, everyday experience. Of every hazard covered in this story, this next one is the strangest, because it does not feel like a hazard at all when you first hear it. It sounds, if anything, like a gift, a loophole, a way for a mortal, short-lived crew to survive a journey that would otherwise take tens of thousands of years. And in a narrow, technical sense, it is exactly that. But the fine print attached to this particular gift may be the most quietly devastating consequence in this entire script. The underlying physics comes from Albert Einstein's theory of special relativity, published in 1905, one of the most thoroughly tested and confirmed frameworks in the history of science. Among its stranger consequences is a phenomenon called time dilation. As an object's velocity approaches the speed of light, time itself, as experienced by that object, slows down relative to an observer who remains stationary. This is not a metaphor, and it is not a rounding error. It has been measured directly, repeatedly, using atomic clocks flown on aircraft, using GPS satellites that require constant relativistic correction to remain accurate, using particles in accelerator experiments that live measurably longer. From an outside observer's perspective, the closer they travel to light speed. The effect is real, precisely quantified, and completely unavoidable for anything with mass moving at extreme velocity. Here is where the physics starts to feel, briefly, like good news. A crew traveling at a sufficiently high fraction of the speed of light would, from their own perspective, experience the passage of time far more slowly than the 26,000-year journey a stationary observer back on Earth would measure. Physicists studying theoretical relativistic travel have calculated that a ship capable of maintaining a constant acceleration near the limits of what a human body can tolerate could, in principle, reach a meaningful fraction of the speed of light and, from the crew's own subjective experience, complete a journey to the galactic center in a span of decades rather than tens of thousands of years. Time dilation, in other words, appears to offer exactly what every other hazard in this story has denied: a shortcut, a way to compress an impossible duration into something a human lifetime might actually contain. But time dilation does not slow time down everywhere. It only slows it down for the traveler. Back on Earth, for everyone who did not leave, time continues to pass at its ordinary rate, the full 26,000 years, grinding forward exactly as it always would have. This is not a paradox. It is the entire, precisely measured point of the effect. The crew experiences a compressed, survivable journey. Everyone and everything they left behind experiences the full, uncompressed span of time in the interim. Consider what that actually means in human terms. A crew departing Earth today, even under the most optimistic version of this scenario, one where every propulsion problem covered earlier in this story has somehow been solved, would return or arrive to find a version of Earth 26,000 years removed from the one they left. Every institution that sent them would be gone. Every language spoken at launch would have changed beyond recognition, the way modern English bears only a distant resemblance to the language spoken in Britain a mere 1,000 years ago, let alone 26 times that span. Every government, every culture, every technological framework the mission was built within would have dissolved, evolved, and been replaced by something the crew has no context for understanding. In the most literal sense possible, they would not simply be far from home. They would be visitors from a version of humanity that, from the perspective of whatever exists on Earth at that point, is closer to ancient history than living memory. This is the trap embedded inside the gift. Time dilation genuinely does solve the crew's personal, biological problem of surviving a subjectively short version of an impossibly long journey. It does nothing to solve, and in fact actively worsens, the problem of connection, continuity, and return. A crew that successfully uses relativistic time dilation to survive the trip has, by the same physics that saved them, permanently and irreversibly severed themselves from everyone and everything they knew. There is no return flight that resets this cost. Traveling home would simply compound it further, adding another span of dilated but still enormous elapsed time on top of the first, guaranteeing that whatever Earth the crew eventually returns to bears even less resemblance to the one they departed. Physicists sometimes describe this using a phrase borrowed from an old thought experiment, the twin paradox, first explored in the early 20th century as a way of testing the logical consistency of special relativity itself. One twin stays on Earth. One twin travels near the speed of light and returns. When they meet again, the traveling twin is immeasurably, physically younger than the twin who stayed behind, exactly as the mathematics predicts, confirmed experimentally many times over in the centuries since. It is a clean, elegant demonstration of real physics. It is also, quietly, one of the loneliest ideas in the entire field, because it describes, with total precision, exactly how a person could survive impossible distances and lose everything that made surviving worth doing in the first place. There's a subtlety within the physics itself worth pausing on, because it explains why this effect is not simply a matter of perspective, the way some popular explanations mistakenly suggest. Time dilation, as experienced by the traveling crew, is not symmetrical with what an observer on the ship would calculate for Earth. The asymmetry exists because the ship, unlike Earth, has to accelerate, decelerate, and change its state of motion to make the journey at all, breaking the symmetry that would otherwise apply if both parties simply drifted past each other at constant velocity. This is precisely what resolves the so-called paradox at the heart of the effect. It is not a matter of who is really moving, but a real, physical, measurable difference in the elapsed time experienced by an object that has undergone acceleration versus one that has not. The traveling crew's clock runs slow relative to Earth's, not because of any illusion of perspective, but because of a genuine, asymmetric difference in the paths each side took through space and time. There's one hazard left in the propulsion and physics portion of the story, one that shifts the focus away from the ship itself and onto the people inside it, and the question of what it actually takes to keep a crew, or many generations of crew, functioning across a journey this long. Every hazard covered so far in this story assumes, in some sense, a single crew, departing once, experiencing the journey directly, and either surviving or not. But a journey spanning tens of thousands of years, even with time dilation compressing the crew's subjective experience into mere decades, still requires solving a problem that has nothing to do with physics at all. It requires figuring out how to keep human beings, and everything human beings depend on, functioning as a closed, self-sufficient system for a span of time longer than any human institution in recorded history has ever managed to survive intact. This is the concept researchers call a generation ship, a vessel large enough and self-sufficient enough to support not a single crew completing a mission within their own lifetimes, but multiple successive generations, born, raised, and eventually dying aboard the ship itself, with the original mission's arrival point reached only by descendants, many generations removed from whoever originally departed. The concept has circulated in serious scientific literature since at least the early 20th century, when physicist Robert Goddard, better known as a pioneer of American rocketry, sketched out early theoretical considerations for exactly this kind of multi-generational interstellar travel. The logistics involved are staggering in their own right, entirely separate from anything covered earlier in this story. A generation ship needs a closed-loop life support system, one capable of recycling air, water, and waste with near-perfect efficiency for centuries or millennia, without any possibility of resupply from outside. Even small inefficiencies compound catastrophically across that timescale. A recycling system that loses just a fraction of a percent of its water or oxygen per year, a rate that might be entirely acceptable for a mission lasting a decade, would exhaust its reserves entirely well before a journey measured in centuries reached its midpoint. Every component of the ship's biological support systems would need either a genuinely unlimited operational lifespan, something no engineered system in human history has ever achieved, or a fully self-sufficient manufacturing and repair capability, meaning the ship would essentially need to carry and maintain indefinitely its own industrial base. Then there is the population itself, and the genetics involved in keeping a closed human population viable across dozens or hundreds of generations. Population geneticists studying this exact question have found that avoiding the compounding effects of inbreeding within an isolated population requires a founding group considerably larger than popular science fiction typically imagines. Not the handful of families a small ship might comfortably house, but numbers reaching into the multiple thousands, in order to maintain sufficient genetic diversity across the number of generations such a voyage would actually require. A ship too small, populated by too few founders, would face a genetic bottleneck problem that compounds with every generation, gradually narrowing the population's genetic diversity until health problems begin appearing at rates far beyond anything found in even geographically isolated human populations on Earth. Beyond biology, there is the question of culture, governance, and continuity of purpose. Arguably, the least quantifiable and most fragile part of the entire proposition. Every human institution in recorded history that has attempted to maintain a consistent mission, structure, or set of values across multiple centuries has eventually failed to do so in its original form. Religions have splintered, empires have dissolved, even relatively young institutions, universities, and governments measured in mere centuries rather than millennia have undergone transformations so complete that their founders would barely recognize them today. A generation ship asks something history has no successful precedent for: that a closed population, isolated from any outside contact or correction, maintain not just physical survival, but a coherent sense of shared purpose, sufficient to keep successive generations committed to completing a mission none of them personally chose, for a span of time longer than civilization itself has existed on Earth. Consider what it would mean, practically, for someone born several hundred generations into such a voyage. they would never have seen Earth. They would never see the destination either, unless the mission timeline placed their birth near its very end. Their entire understanding of home would be the interior of a vessel, its corridors and compartments, the only physical reality they had ever known or would ever know. The mission's purpose, something inherited rather than chosen, potentially maintained across that many generations more as ritual and obligation than lived conviction. Whether human beings or any social structure human beings are capable of building can actually sustain purpose and cohesion across that kind of multi-century isolation remains, honestly, an open question, one without a clear answer in either direction, because nothing in recorded history has ever attempted anything remotely close to the scale of sustained isolation. There are, at least, imperfect historical parallels worth considering, even if none of them approach the true scale of a generation ship. Isolated island populations, monastery communities maintaining a single doctrinal tradition across centuries, even long-running scientific research stations in Antarctica offer small, partial glimpses of what sustained isolation does to a human group over time. Each of these examples involves populations far larger, environments far less confined, and durations far shorter than a true multi-century interstellar voyage would require. Yet even these comparatively modest cases show measurable drift. Language changes, social norms shift. Founding purposes are reinterpreted or quietly abandoned by descendants who never chose them. If isolation measured in decades or a few centuries already produces this much cultural drift among reasonably sized, resource-secure populations, a truly closed population sealed inside a metal hull for tens of thousands of years represents a scenario without any genuine historical precedent to draw from at all. This is not a hazard with numbers attached to it, in the way radiation dose or bone density loss can be measured and quantified. It is closer to a structural uncertainty sitting underneath the entire premise of a crude, multi-generational journey, a question mark hovering over every other hazard covered so far, because none of those hazards matter if the ship itself, as a functioning society, cannot hold together long enough to reach its destination in the first place. And even if it does hold together, biologically and culturally, one further hazard remains, one that has nothing to do with logistics or governance, and everything to do with what isolation itself does to a human mind, long before the body or the society around it has any chance to fail. Every hazard covered so far in this story has been physical: radiation striking cells, bone dissolving without gravity's load, dust puncturing hulls at relativistic speed. But the mind is not exempt from the consequences of this journey, and the evidence for what prolonged isolation and confinement actually does to human psychology is neither speculative nor new. It comes from decades of careful observation, gathered from the closest terrestrial analogs available for what a long-duration space mission actually demands of a human being. The most extensively studied of these analogs comes from Antarctic research stations, where small crews live and work in extreme isolation, often for the better part of a year, cut off from resupply, from easy communication, and from the ordinary sensory variety of everyday life. Researchers studying what has come to be called winter over syndrome, a documented pattern observed repeatedly among personnel stationed through the long Antarctic winter, have found consistent, measurable effects: disrupted sleep cycles, difficulty concentrating, increased irritability, and in some documented cases, symptoms consistent with depression and anxiety, emerging even among personnel who were carefully screened and selected in advance specifically for psychological resilience. This detail matters. These are not average individuals placed into isolation without preparation. They're among the most psychologically robust, most carefully vetted people available. And even among that group, sustained isolation still produces measurable strain. Sleep itself becomes a particular casualty. Human circadian rhythms, the internal biological clock governing when the body expects to sleep and wake, evolved around Earth's 24-hour cycle of light and darkness, reinforced daily by direct exposure to sunlight. Remove that daily light cue entirely, replace it with the artificial, unchanging lighting conditions of a spacecraft or a polar research station during months of continuous darkness, and the body's internal clock begins to drift, producing measurable disruptions to sleep quality and duration. NASA's own research into astronaut sleep aboard the International Space Station has documented that crew members frequently sleep less and less restfully than recommended, even during missions lasting only a period of months, well short of anything approaching a multi-year or multi-generational voyage. Then there's the matter of sensory monotony, a factor that sounds almost trivial until you consider how constantly the human mind, evolved across hundreds of thousands of years in a visually and texturally rich natural environment, relies on novel sensory input to remain psychologically stable. A spacecraft interior offers none of that. The same walls, the same lighting, the same recycled air, the same small set of faces, repeated day after day, year after year, for as long as the mission continues. Researchers studying confinement environments have found that this kind of unchanging sensory environment can itself become a source of significant psychological strain over time, sometimes described informally among mission psychologists as a contributing factor to what has been called, somewhat loosely, the third quarter phenomenon, referring to a documented dip in morale and psychological well-being that tends to emerge once a long-duration mission has passed its temporal midpoint, when the initial novelty has fully worn off, but the eventual return still feels distant. Crew dynamics present their own compounding challenge. Small groups confined together for extended periods, without the ability to simply leave or seek distance from one another, have been studied extensively in isolation research spanning submarine crews, Antarctic stations, and long-duration space analog missions, such as NASA's HERA and Mars Analog Habitat programs. These studies have consistently found that interpersonal friction tends to increase over time in sustained close-quarters confinement, even among crews initially selected specifically for compatibility and psychological stability. Conflict management, communication protocols, and structured personal space become not peripheral concerns, but central operational requirements, addressed as seriously as any purely technical system aboard the vessel. Now extend all of this, not across the months typically studied in these terrestrial analogs, but across the years, decades, or generations a true journey to the galactic center would require. The available research offers a clear, well-documented picture of what happens to human psychology across mission durations we have actually studied. It offers considerably less certainty about what happens across durations we have not, and have, in the entire history of human civilization, never had the opportunity to observe directly. what can be said honestly is this. Every documented trend, sleep disruption, sensory monotony, interpersonal strain, and mood decline tends to worsen, not improve, the longer confinement and isolation continue. There is no evidence in the existing research suggesting these effects plateau or reverse on their own with sufficient time. If anything, the data available points in the opposite direction, toward a psychological cost that compounds rather than resolves, layered on top of every physical and structural hazard already described in this story. There is one more compounding factor worth naming directly, because it separates deep space isolation from every terrestrial analog researchers have studied, even the most extreme ones. Antarctic researchers, however isolated, retain the psychological knowledge that rescue, however difficult, remains theoretically possible, and that regular, if delayed communication with the outside world continues. A crew traveling toward the galactic center loses even that. Communication delay alone becomes an insurmountable psychological barrier almost immediately. A radio signal, traveling at the absolute maximum speed physics allows, would take over 4 years just to reach the nearest star system, and just as long to return, meaning any real-time conversation with Earth becomes impossible within the very first years of the voyage, let alone across a journey measured in tens of thousands of light years. Mission psychologists studying even short delay analogs, such as simulated Mars missions with communication lags of 20 minutes each way, have found that this alone measurably changes crew psychology, shifting communication style, reducing spontaneous emotional expression, and increasing feelings of isolation from mission control, even when a response is guaranteed to eventually arrive. A crew bound for the galactic center would face a communication delay not of minutes, but of tens of thousands of years, rendering the very concept of two-way contact with home meaningless, almost from the moment of departure. This closes the circle on everything covered so far, from the ship's environment down to the individual human mind inside it. What remains is the destination itself, the place all of these hazards have been building toward, and the very different, very strange set of conditions waiting at the actual center of the galaxy, assuming, against every obstacle described until now, a ship somehow arrives at all. Assume, for a moment, that every hazard covered so far has somehow been survived, the radiation managed, however imperfectly, the fuel problem solved by some fuel source beyond anything currently available, the body sustained across the crossing, the ship's society held together, the minds inside it intact enough to keep functioning. Assume the ship, against every obstacle in this story, is finally approaching its destination. What waits there does not resemble the empty corridor of space the ship has been crossing for the entire journey until now. It resembles something else entirely. The outer regions of the Milky Way, where our own solar system sits, are sparse by galactic standards. Stars average several light years apart, vast gulfs of near-total emptiness separating one point of light from the next. This spacing is not uniform across the galaxy. As a ship approaches the true galactic center, that spacing collapses dramatically. Astronomers studying the region immediately surrounding Sagittarius A star have found that the central cubic parsec, a volume of space representing a vanishingly tiny fraction of the galaxy's total size, contains roughly 10 million stars. To put that in a comparison that actually registers, a parsec is only about 3.26 light years across. Packing 10 million stars into a volume that small means the average distance between neighboring stars near the galactic center shrinks to a small fraction of a light year, compared to the several light years typical of our own neighborhood. Stars that, from Earth's vantage point, would be considered impossibly close encounters become, near the galactic core, simply the local, everyday spacing of the neighborhood. This density brings its own category of hazard, entirely separate from anything covered earlier in the empty stretches of interstellar space. Close stellar encounters, vanishingly rare in the outer galaxy, become a routine possibility near the core. Astronomers have documented individual stars in this region, locked into extraordinarily tight orbits around Sagittarius. A star itself, with some, such as the star cataloged as S4714, making close approaches to the black hole at distances comparable to how near Saturn gets to our own sun, while traveling at speeds reaching roughly 8% of the speed of light. A ship navigating this environment would be threading a genuinely crowded stellar traffic pattern, one where the gravitational influence of nearby stars and the sheer statistical likelihood of a close pass with one of them becomes a real navigational hazard rather than a remote theoretical concern. Beyond the raw density of stars, the composition of the neighborhood itself changes near the galactic center. While most of the stars in this dense central cluster are old red giants, astronomers have also identified more than 100 massive, young, hot stars in the immediate vicinity, including a category known as Wolf Rayet stars, among the most luminous and violently active stars known to exist. These stars are notable not just for their brightness, but for the sheer intensity of the stellar wind they generate. Streams of charged particles blown outward at extreme velocity, adding yet another source of high-energy radiation to an environment already saturated with it. Their presence near the galactic center was, according to researchers who study the region, something of a genuine surprise, since the immense tidal forces exerted by a supermassive black hole were expected to prevent new star formation from occurring so close to it in the first place. Exactly how these young massive stars formed in such a gravitationally hostile neighborhood remains an active area of ongoing astrophysical research, one of the genuinely open questions this story has to leave honestly unresolved. There is a further layer to this environment worth understanding before a ship ever gets close enough to see any of it directly. Beyond the crowded stellar neighborhood itself, astronomers have identified enormous structures extending far above and below the galactic plane, centered on the region around Sagittarius A star. First detected through gamma-ray and X-ray observations, these structures, sometimes called Fermi bubbles or E Rosita bubbles, depending on which observational data revealed them, are vast lobes of energetic plasma extending outward as far as 25,000 light-years above and below the galactic center itself, roughly the same order of magnitude as the entire distance from our own solar system to the core. Researchers using increasingly detailed computer simulations have confirmed that these bubbles trace directly back to activity from Sagittarius A star, evidence of the black hole periodically venting enormous quantities of energy outward into the surrounding galaxy, likely the aftermath of past episodes when significantly more matter than usual fell into it at once. A ship approaching the galactic center along certain trajectories would need to account for this structure as well, an additional zone of elevated radiation and energetic particles layered on top of everything else in this already crowded environment. Consider then what arrival at the galactic center actually means, practically, for a ship that has survived every hazard covered until this point. It is not a quiet destination waiting patiently at the end of a long, empty road. It is one of the most crowded, most energetic, most actively hostile stellar environments anywhere in the galaxy. Dense with radiation sources, dense with gravitational complexity, dense with the kind of close stellar traffic that simply does not exist anywhere along the outer regions of the journey a ship would have already crossed. Arrival does not mean the hazards end. In many ways, arrival is where an entirely new category of them actually begins. And even this crowded, radiation-soaked neighborhood of stars is not the final hazard waiting at journey's end. At the exact center of that stellar traffic sits the object the entire journey has been oriented toward from the very beginning, a supermassive black hole whose gravitational influence a ship would begin to feel long before it ever came close enough to see anything resembling an event horizon. At the center of that crowded stellar traffic sits the object this entire journey has been oriented toward since the very first section of the script. Sagittarius, a star, the supermassive black hole anchoring the Milky Way. And here, the physics offers something genuinely surprising, a detail that runs against most people's intuitive expectations of what a black hole encounter would actually feel like. Start with the numbers themselves, because they establish the scale of what a ship would actually be approaching. Sagittarius, a star, carries a mass of approximately 4 million times that of our own sun, confirmed through decades of careful observation, most directly through the orbital tracking of stars like S2, whose 16-year orbit around the object allowed astronomers to calculate its mass with remarkable precision. All of that mass is concentrated within a region defined by what physicists call the Schwarzschild radius, the boundary beyond which nothing, not even light, can escape the object's gravitational pull. For Sagittarius, a star, that radius measures approximately 12 million kilometers, or about 8/100ths of an astronomical unit. To put that in a comparison that actually registers, that distance is smaller than the gap between Mercury and the Sun at its closest approach. An object with the mass of 4 million suns, compressed into a region smaller than the innermost orbit of our own solar system. Now here is where intuition tends to mislead people. Popular imagination, shaped heavily by dramatic depictions in fiction, tends to picture a close encounter with any black hole as instantly and violently fatal, the body torn apart by gravity the moment it gets anywhere close. For smaller, stellar mass black holes, the kind formed from the collapse of a single dying star, this instinct is largely correct. Because their mass is compressed into an extremely small volume, the difference in gravitational pull between one end of an approaching object and the other, a difference called tidal force, becomes lethally extreme at a relatively large distance, stretching anything nearby into a thin strand of material long before it reaches the event horizon itself, a process astrophysicists have informally nicknamed spaghettification. Supermassive black holes, despite containing vastly more total mass, behave completely differently in this specific respect, and the reason comes down entirely to scale. Tidal force depends not just on an object's total mass, but on how sharply gravity changes over a given distance, and for a black hole as physically large as Sagittarius, a star, With an event horizon spanning millions of kilometers rather than mere kilometers, that gravitational gradient near the horizon is actually far gentler than it is around a small, stellar mass black hole. A hypothetical traveler approaching Sagittarius A star would, according to the physics, be able to cross the event horizon itself without experiencing immediately lethal tidal forces, something that would be physically impossible around a smaller black hole, where spaghettification occurs well before the horizon is ever reached. This is one of the more genuinely counterintuitive facts in this entire story. The more massive the black hole up to a point, the gentler its immediate tidal environment actually becomes near the horizon, even as its overall gravitational influence across the surrounding region of space grows correspondingly larger. It's worth pausing on how confident scientists actually are in these mass and distance figures, because the certainty here did not come easily. Confirming that Sagittarius A star was, in fact, a black hole, rather than some other exotic but non-collapsed object, took decades of painstaking observation. Reinhard Genzel and Andrea Ghez, whose separate teams tracked S2 and other nearby stars for the better part of 30 years combined, were awarded the Nobel Prize in Physics in 2020, specifically for demonstrating that the mass concentrated at the galactic center could not be explained by any configuration of ordinary matter, stars, gas, or dust. It had to be compressed into a volume small and dense enough that only a black hole satisfied the mathematics. This is part of why the counterintuitive detail about tidal gentleness matters so much for the story we're telling tonight. It is not speculation or convenient plot device. It follows directly from the same rigorously measured mass and radius figures that took 3 decades of dedicated observation to establish beyond reasonable doubt. This does not mean a close approach to Sagittarius A star would be survivable in any practical sense, and it's important not to let this counterintuitive detail soften the larger picture. Crossing the event horizon of any black hole, regardless of tidal gentleness at that specific boundary, means crossing into a region from which no signal, no matter, no information of any kind can ever return. Whatever happens beyond that boundary, according to general relativity, becomes permanently and completely inaccessible to the rest of the universe. In addition, long before a ship ever reached the event horizon itself, it would need to survive passage through the superheated, violently active environment immediately surrounding the black hole, an environment shaped not by tidal forces, but by something else entirely: the extraordinary temperatures and radiation produced by matter falling into the black hole from the surrounding accretion disk. In May of 2022, the Event Horizon Telescope collaboration released the first direct image of Sagittarius A star, assembled from data gathered by a network of radio observatories spanning the entire globe, working together to create a virtual telescope roughly the size of Earth itself. What that image revealed was not the black hole directly, since by definition, no light escapes it to be photographed, but the glowing ring of superheated material surrounding it, plasma reaching temperatures in the range of 10 billion degrees, tracing the outline of the black hole's shadow against that hot, luminous backdrop. That superheated ring and everything happening within it represents the true final hazard waiting at the literal center of this entire 26,000 light-year journey, and it is, in its own way, more immediately dangerous than the black hole's gravity itself. Arrival in this story does not mean calm. It means reaching the single most energetic, most violently active environment anywhere in the galaxy. A region where the black hole itself is only one piece of a much larger, much more immediately dangerous picture. Sagittarius, a star, is not a passive object, quietly sitting at the center of the galaxy. It is, at least intermittently, an actively feeding one, and the process of matter falling into a black hole generates radiation on a scale that dwarfs anything discussed earlier in this story. NASA's Chandra X-ray Observatory, which has monitored the region around Sagittarius A star for years, recorded something remarkable in 2015. A colossal X-ray flare, roughly 400 times brighter than the black hole's typical output. An eruption so dramatic that astronomers initially considered whether it might represent a small asteroid being torn apart and consumed, or an unusually dense clump of gas from the surrounding accretion flow suddenly spiraling inward. These flares are not rare, isolated events either. Chandra's long-term monitoring campaign has documented daily flares of moderate brightness occurring routinely, punctuated by rarer, far more extreme outbursts, like the one recorded in 2015, evidence of a genuinely unpredictable, highly variable radiation environment immediately surrounding the black hole. The mechanism behind these flares comes from the physics of what astronomers call an accretion disk, a swirling structure of superheated gas and plasma spiraling inward toward the black hole, compressed and accelerated by intense gravitational and magnetic forces as it falls. Friction and magnetic interaction within that disk heat the material to extraordinary temperatures, in some regions reaching into the billions of degrees, hot enough to strip electrons entirely from their atoms, producing a form of matter called plasma that radiates intensely across the electromagnetic spectrum, from radio waves through visible light and all the way into X-rays and gamma rays. A ship approaching closely enough to study this environment directly would be approaching a radiation source vastly more intense and vastly more erratic than the steady background of galactic cosmic rays that has been the primary radiation hazard for the entire rest of this journey. There is a further complication specific to this region, one involving a nearby molecular cloud complex called Sagittarius B2, sitting a few hundred light years from the black hole itself. Observations using the Integral Gamma Ray Observatory and the Japanese Suzaku X-ray satellite have detected what astronomers interpret as an echo of sorts, X-ray radiation reflecting off Sagittarius B2's dense gas, consistent with a massive outburst from Sagittarius A star that occurred several hundred years ago, its light only now reaching and illuminating this more distant cloud. This detail matters for what it reveals about the black hole's history. Sagittarius A star, quiet and comparatively dim in the present era, appears to have been dramatically more active in the past, at times potentially 1,000,000 times brighter than its current output, based on the intensity of radiation needed to produce the reflected signal now being observed at Sagittarius B2. A ship arriving at the galactic center would have no guarantee of finding it in its current, relatively subdued state. The black hole's activity level fluctuates on timescales far longer than any single human lifetime, and there is no way to know in advance whether a given arrival window would coincide with a period of relative quiet or a period of extreme, potentially lethal outburst. There is one more feature of this environment worth understanding, because it compounds everything already described. The region immediately surrounding Sagittarius A star hosts magnetic fields of extraordinary strength, generated by the same swirling, superheated plasma that produces the X-ray flares. Astronomers studying a magnetar, a particular kind of extremely magnetic neutron star, discovered orbiting close to Sagittarius A star in 2013, have used it as a natural probe of the region's magnetic environment, finding field strengths far beyond anything found near Earth or anywhere else easily accessible to study. These intense magnetic fields interact directly with the charged particles streaming outward from the accretion disk, channeling and accelerating them further, adding yet another layer of high-energy particle radiation to an environment already saturated with X-rays, gamma rays, and the visible aftermath of the black hole's own feeding activity. A ship's shielding, already stretched to its practical limits, managing galactic cosmic rays across the outer journey, would face a qualitatively different and considerably more intense challenge in this final environment, one where multiple overlapping radiation sources compound simultaneously, rather than arriving as the relatively steady, singular background hazard present throughout most of the crossing. Consider what this means for the entire premise of Arrival itself. Every hazard covered throughout this story, radiation, dust, fuel, time, isolation, has been a problem to be endured, managed, or minimized across the duration of the crossing. The environment immediately surrounding Sagittarius A star is different in kind. It is not a hazard to be endured for a fixed period and then left behind. It is the permanent, ongoing condition of the destination itself, a region of space that does not become safer once a ship arrives, because arrival places the ship directly inside one of the most energetic environments the galaxy has to offer, with no guarantee that the flare activity observed by Chandra, or the outburst history revealed at Sagittarius B2, would happen to be quiet during the exact window a ship finally completed its 26,000 light-year journey. This, then, is the honest shape of the full picture. 22 distinct hazards, each verified, each measured, each drawn from real science rather than speculation, stacked one after another across a journey that begins the moment a ship leaves Earth's magnetosphere and does not meaningfully end until, or unless, it somehow survives all the way to the most energetic environment the galaxy contains. What remains now is not another hazard. It is the question every one of these hazards has been building toward from the very beginning. What, if anything, would actually be left of the traveler by the time any of this became relevant at all? Return, for a moment, to the very beginning of this journey, to the person who first stepped aboard the ship, before any of the hazards described in this story had a chance to act. Now consider what remains of them, hypothetically, at the far end of a crossing measured in tens of thousands of years, assuming, against every obstacle already covered, that something of the mission actually reaches its destination. Radiation has been accumulating the entire time, silently, continuously, a dose that never fully resets, layered across whatever fraction of the journey a single human body might have personally experienced before handing the mission forward to a new generation. Bone density, weakened from the earliest months without gravity's steady pull, never fully recovers even under the most careful medical attention available. Muscle mass, eroded at a rate current countermeasures can only partially offset, would have been renegotiated by the body's own chemistry generation after generation, across a mission with no clear precedent for what multi-century or multi-millennial biological adaptation to a closed, artificial environment might actually produce. Whether human physiology reaches some new equilibrium under these conditions, or simply continues degrading indefinitely, remains, honestly, one of the deepest open questions raised across this entire story. A question no experiment has ever run long enough to answer. Then there is the matter of who, precisely, would be arriving. If the journey uses relativistic time dilation to compress a traveler's subjective experience into a survivable span, that traveler returns, or arrives, into a version of the outside universe utterly disconnected from the one they departed. If the journey instead relies on generational succession, the person who eventually reaches the destination was never the person who left at all. They are a descendant, many hundreds of generations removed, born into a ship whose original purpose has been transmitted to them as inheritance rather than choice, shaped by a culture, a language, and a set of assumptions that would likely be unrecognizable to whoever first stepped aboard at the very start. In either version of this story, and there is no third option physics currently allows, the traveler who arrives is not, in any meaningful sense, the same person or even the same kind of person as the one who departed. Consider what that means for the entire premise underlying a journey like this. Every version of reaching the center of the galaxy that current physics permits requires giving up something essential about continuity itself. Either continuity with the world left behind, severed by relativistic time dilation, or continuity with the individual traveler, dissolved gradually across generations of shipboard succession. There's no version of this journey using any technology grounded in real, established science, where the same person who leaves Earth also arrives at Sagittarius, a star, still connected to the world, the relationships, and the identity they started with. The scale of the distance does not just challenge the body, it challenges the very idea of a single continuous journey undertaken by a single continuous self. This is, in its own way, the deepest hazard uncovered across this entire story. Deeper than radiation, deeper than fuel limits, deeper even than the black hole waiting at the destination itself. Every other hazard describes a way the journey might fail. This one describes something stranger, a way the journey might, technically, succeed, and still cost the traveler almost everything that made the idea of arriving matter in the first place. A ship might reach the galactic center, Sagittarius. A star might, in some far distant future, actually be observed up close by something built by human hands. But whoever, or whatever, is aboard that ship when it finally arrives will have paid for that arrival with a version of continuity no return trip, no message home, no reunion could ever restore. There is a strange comfort hidden inside that thought, if you sit with it long enough. Every human being who has ever lived has already been separated, gradually, from every earlier version of themselves. The person reading these words is not, in any strict physical sense, the same collection of cells that existed a decade ago or even a year ago. Memory, habit, and a continuous thread of subjective experience are what stitch those different versions together into something that feels like a single, unbroken self. A journey to the galactic center simply stretches that same ordinary, everyday process of becoming someone slightly different, across a scale large enough to become impossible to ignore. What normally happens quietly, across a single lifetime, barely noticed would happen instead across thousands of lifetimes, laid end to end, each one slightly further from where the story began. Think too about what the ship itself would carry beyond fuel and shielding and closed-loop life support. It would carry whatever the original crew chose to bring with them. Records, images, languages, a version of history frozen at the moment of departure. Across generations or across a single relativistic leap forward in time, that inheritance would drift, reinterpreted, partially forgotten, partially transformed into something new, the way any inherited story changes slightly with each retelling. By the time anything resembling arrival occurred, the ship's own understanding of why it had ever left in the first place might itself have become a kind of legend, half history and half myth, the founding purpose preserved less as precise fact than as a shape everyone aboard still recognized, even if the details had softened at the edges. There is something almost gentle in recognizing this plainly, rather than dressing it up as tragedy or triumph. It is simply what the physics, the biology, and the arithmetic of this journey actually require. Distance of this magnitude does not merely separate 2 points in space. It separates a person from every version of themselves that time, generations, and relativity would inevitably carry them away from, long before any destination ever came into view. Bring everything in this story back together one final time and look at the whole shape of it at once, the way you might step back from a long journey and finally see the entire road behind you, rather than the single step in front of your feet. It begins with an address discovered by accident in 1932 by a young engineer chasing static on a phone line, later confirmed with decades of patient, careful astronomy, and finally photographed directly in 2022, a soft, glowing ring of light surrounding a shadow 26,000 light years from where you are right now. It continues with the shield every human being has always lived beneath without noticing, the magnetosphere and atmosphere working together to make an entire evolutionary history possible. And the moment that shield disappears, the instant a ship leaves it behind. It moves through radiation that falls like rain and never stops. A dose that triples the moment Earth's protection ends and continues accumulating for every year of the crossing, measured against career limits that a single round trip to Mars would already exhaust. It runs through shielding that helps only up to a point, and then, past that point, quietly begins making the problem worse instead of better. A ceiling built directly into the physics of how matter interacts with the highest energy particles in the galaxy. It moves through a body that begins forgetting, cell by cell, what gravity had spent hundreds of millions of years teaching it to expect. Bone dissolving at a rate that turns 6 months in orbit into a year of elderly decline, muscle eroding even under the most careful medical supervision available. It runs through dust grains turned into artillery shells by sheer velocity, and gas turned into radiation by the same relentless physics. A wind made of atoms instead of air, both problems worsening the faster a ship tries to escape them. It runs through fuel, and the stubborn 19th century mathematics that no amount of ambition has ever found a way around. Chemical propulsion capped at a fraction of 1% of light speed. No matter how much is thrown at the problem, antimatter offering a way past that ceiling only by introducing a danger nearly as severe as the one it solves. It runs through time itself, bending in exactly the way Einstein's equations predicted more than a century ago, offering a crew the gift of a survivable subjective journey, while quietly severing every connection to whatever they left behind. it runs through the almost impossible logistics of keeping a closed society intact across spans of time longer than any human institution has ever managed, and through the quieter, harder to measure cost of isolation itself, the mind fraying slowly under conditions no laboratory on Earth has ever been able to fully simulate. And at the very end of all of it, it runs into a destination that offers no rest at all. 10 million stars packed into a volume smaller than anything found near our own solar system. A black hole whose gravity turns out to be gentler at the threshold than smaller black holes, yet surrounded by flares 400 times brighter than its ordinary output. An environment that was, at some point in its own history, up to 1,000,000 times more energetic than it appears today. 22 hazards, each one real, each one measured, documented, drawn from actual instruments, actual observations, actual physics rather than invention. None of them individually insurmountable in isolation, and all of them laid end to end across a distance this vast, compounding into something that current science has no answer for and may never have one. Not because the destination is unreachable in principle, but because the road there asks more of a human body, a human mind, and a human civilization than any of them have ever been asked to give before. Consider, too, how the hazards themselves refuse to stay separate from one another, the way a tidy list might suggest. Radiation compounded with time, because the longer a crossing took, the more dose accumulated, and every attempt to shorten that duration by increasing speed only intensified the dust and interstellar wind waiting outside the hull. The fuel problem compounded with the body's decline, because a slower, more survivable acceleration profile meant a longer exposure to every biological hazard already described, while a faster one asked the body to endure forces closer to its physical limits. Isolation compounded with the ship as civilization problem, because a mind fraying under sensory monotony is not a mind well suited to the delicate, generations-long work of preserving culture, purpose, and cohesion across a population sealed inside a single vessel for longer than recorded history has ever lasted. Nothing on this list ever behaved as a single, contained obstacle. Everything touched everything else. And that compounding is, in its own way, the truest lesson buried inside this entire story. A journey like this was never going to fail because of one dramatic, singular catastrophe, the kind of moment a film might dwell on. It was always going to fail, if it failed, the way most real things fail, gradually, quietly, from the slow accumulation of many small, individually survivable problems, each one chipping away at the margin of safety the others depended on, until the sum of them became larger than anything a single hazard, considered alone, could ever have suggested. It helps, before walking back through the whole road one last time, to remember how this story actually started. Not with a spacecraft, not with an equation, with a present tense scene, a small window, and a number so large it stopped behaving like distance and started behaving like time. Everything since then has simply been an answer to the question that opening scene posed without quite saying it out loud. What would it actually take, in real, measured, verified terms, to cross a gap that size? The honest answer turned out to be longer, stranger, and more layered than any single hazard could have suggested on its own. And somewhere in the middle of all of it, easy to lose beneath the numbers and the physics, is the simplest fact of all. The question was never really about distance. It never was. Distance was only ever the backdrop the rest of this story unfolded against. The stage, not the danger. What actually gets you on a journey like this is never the 26,000 light years themselves. It is everything living inside those light years, waiting patiently, one hazard at a time, for a traveler who was never quite built to survive the crossing in the first place. There is a particular kind of quiet that settles over a story once every piece of it has finally been laid out. Not the quiet of an ending exactly. Something closer to the quiet of having walked the entire length of a very long road and finally arriving somewhere you can stand still and look back. You began this story sitting behind a small window, looking out at stars that have not visibly moved in your lifetime. 26,000 light years away, a supermassive black hole waits at the exact center of the galaxy you were born into, confirmed by decades of patient observation. Photographed for the first time in 2022, its mass and its distance now known with a level of precision that would have seemed impossible to Carl Jansky, hunched over his rotating antenna in a New Jersey field in 1932, listening to static he could not yet explain. Everything between that opening image and this closing one has been an honest accounting of what actually stands in the way. Not one dramatic obstacle, but 22 of them, each real, each drawn from instruments that have already flown, from data that has already been gathered, from physics that has already been tested and confirmed, radiation that falls without ever stopping, a body that forgets, slowly, what it was built to do, dust turned lethal by sheer velocity, fuel that no amount of ambition can multiply past a hard mathematical ceiling, time itself bending exactly as predicted, offering escape from distance only by demanding disconnection in return. A society asked to hold itself together longer than any society in recorded history ever has. A mind asked to remain whole inside a silence deeper than anything human psychology has ever been fully tested against. And at the very end of all of it, should anything ever actually arrive, a black hole surrounded by flares 400 times brighter than its usual quiet hum, an environment that offers no rest, only a different, more concentrated version of the same danger that shaped every mile of the journey before it. There's a strange comfort available in numbers this large, if you let yourself sit inside them rather than flinch away. 26,000 light years is not a distance designed to make you feel small in a cruel way. It is simply a fact about the size of the structure you happen to live inside. One galaxy among hundreds of billions. One solar system among hundreds of billions more within that single galaxy alone. One small, rocky, gravity-anchored world circling one ordinary, unremarkable star, roughly 2/3 of the way out from a center so violent and so bright that nothing built by human hands has ever survived a close approach to it, or ever will, using any technology grounded in physics as we currently understand it. And yet, from exactly here, tucked safely inside that vast structure, protected by a magnetic field you have never had to think about, and an atmosphere billions of years in the making, you can still look up on a clear night and see a faint band of light stretching across the sky. The combined glow of hundreds of billions of stars seen edge on, the same galaxy this entire story has been describing, viewed from the one vantage point inside it that happens to be survivable. That faint band of light is not a postcard from somewhere else. It is a picture of home, taken from the inside, by a species that has never needed to leave in order to understand, with remarkable precision, exactly what waits at the center of it. Consider, too, what it means that we know any of this at all. Every fact laid out across this story, the mass of the black hole, the distance to it, the radiation dose of a Mars mission, the exact year Jansky first heard that faint, unexplained hiss, exists because human beings, working patiently across generations, pointed instruments at the sky, and were willing to wait decades for an answer. None of them ever needed to survive the journey themselves to understand what waited at the far end of it. Understanding, it turns out, does not require crossing the distance. It only requires paying close enough attention to whatever light happens to reach you from 26,000 years away, and trusting that the universe, vast and largely indifferent as it is, was at least willing to let that light arrive. There is one last comparison worth sitting with, one final way to feel the shape of everything this story has covered. If the entire 26,000-year age of human civilization, from the first cave paintings to the device this story is currently playing through, were compressed into a single hour, the crossing described tonight would take up that entire hour and then keep going, past the edge of the clock into a second hour, and likely well beyond it, before a ship moving at anything resembling currently achievable speed ever glimpsed its destination. Every hazard described across every section of this story would have to be endured without interruption for that entire span. Not once. Continuously. That is the true shape of the distance this story has been describing since its very first sentence. And it is also, in its own strange way, the reason none of it needs to keep you awake tonight. None of this was told to frighten you, and none of it was softened to comfort you either. It was simply told the way the evidence actually points. Because sleep and comfort and the particular stillness this kind of story is meant to offer were never going to come from pretending the universe is smaller or gentler than it actually is. They come instead from something quieter. The simple, settled feeling of finally understanding the true shape of a thing that once seemed unknowable, and finding that understanding, however vast and however humbling, is itself a kind of rest. You are not on that ship. You will most likely never need to survive galactic cosmic rays, or watch your own bones thin month by month, or wonder whether the version of Earth you return to still exists in any recognizable form. You are here, on a small, shielded, gravity-anchored world, wrapped in a magnetic field you have never had to think about, breathing air and atmosphere spent billions of years assembling on your behalf, under a night sky that, for all its darkness, has never once asked you to survive it directly. That is where this story leaves you. Not at the center of the galaxy, and not aboard the ship that could never quite reach it. Here instead, on the one world in this entire 26,000 light-year story that never demanded anything of you at all, simply to close your eyes and let the distance stay exactly where it belongs. Far away. Quiet. Someone else's problem for tonight.